Hi class. In this lecture here, what we want to do is we want to talk about continuity and one-sided limits. So continuity in the mathematical sense has very much the same definition as you would think about it like in a dictionary, right? Like, you know, when something is continuous, you're thinking of like no interruptions, no jumps, no breaks, something like that. So I'm going to show you the mathematical terminology for that. And so one-sided limits is the next topic we're going to talk about. And so when you think about limits, right, like when we evaluated a limit, we looked at both sides. So the limit as x approaches, you know, some value c, and we looked at the limit as both sides. So one-sided limits just look at, you know, obviously just one side of the limit. Okay, so what we're going to do here and what this section is about, we're going to determine continuity at a point and continuity at an open interval. Then we're going to determine one-sided limits and talk about how we use those to determine continuity at a closed interval. And then really the last thing we're going to talk about is how to use something called the intermediate value theorem. Okay, so first off, what is the definition of continuity? So in mathematics, the term continuous has much the same meaning, as I said, as it has in everyday use. So informally, okay, we say that a function f is continuous at some x of c, at some x is equal to c. So this is at a point, okay? It means that there is no interruption in the graph of f at x is equal to c. So that is, its graph is unbroken, it has no holes, no jumps, or no gaps. So you can really think about it as like if a graph is continuous at some x is equal to c, if you have this nice smooth, you know, you can trace your pen along it. So here, if this is c, it's like, oh yeah, my pen goes right through it, no problem. So formally, okay, this is how you determine continuity at a point, and I'm going to show illustrations of all this in a second. A function is continuous at some value c if these three conditions are met. So if any one of these conditions fail, it's not continuous at this point. So f of c is defined, okay? So it's not like there's a hole in the graph. The limit as x goes to c of f of x, it exists, and the limit as x goes to c of f of x is exactly f of c, okay? So for being continuous on an open interval, a function is continuous on an open interval from a to b if the function is continuous at every point in that interval. Okay, so a function that is continuous on the entire real number line from negative infinity to infinity is everywhere continuous. All right, so on the next slide here, let me show you some examples of this stuff failing here, okay? So here are the three conditions, okay? So three conditions exist for which the graph of f is not continuous at x is equal to c. So here are those like counter examples to this. So the first one is f of c is defined. Well, if you look here in this first graph, okay, there's a hole in it, okay? So this is that example where there's a hole. Okay, so that's not good. The second issue here is that the limit as x goes to c of f of x has to exist. So if you look at this graph here, okay, if you look at the limit as x goes to c, you can see that it doesn't exist, right? So the limit as you go this way from above, it's equal to this value. The limit as you go from below, it's equal to this value. So the limit doesn't exist. So here's this example where the graph jumps. It goes like whoop, and then it jumps down here. So these are all cases where it's not continuous at c, right? Like there's a hole in it. It's like it jumps. So, you know, my pen has to pick up to go to the next one. And then the last one here is that the limit as x goes to c of f of x has to be equal to f of c. Well, if you look here, right, this is what f of c is. But if you look here, the limit as x goes to c goes to this value here. So they're not the same here. So again, you have this little jump here, okay? Okay. So these are all cases where it's not continuous. So to be continuous at a point, you need to have all three of these hold, okay? All three of these hold. So like let's look at this figure, this here. Okay, so the figure below shows the graph of some function f. At which numbers is f discontinuous and why? Okay, so let's look here, right? Look at this first one. We have discontinuity at, and the first one we see here is at x is equal to 1, okay? And this is because f of 1 is not defined. Okay, so that's no good right there. Then the next one here is, look, you see at x is equal to 3, it jumps, it goes to here, and then whoop, right here. So the next one is at x is equal to 3. And this is because we see here that the limit as x goes to 3 of f of x, it does not exist, okay? So, you know, the one-sided limits here don't agree. And then finally, look at x is equal to 5. There's a hole in it, but the graph jumps up here. So this here, we have discontinuity at x is equal to 5 because the limit as x goes to 5 of f of x, look, f of 5 is defined up here, so it's not equal to f of 5. So here's another example where you see all three of these fail. Okay, so this is when it talks about discontinuity. All right, let's talk about these here. Okay, so where are each of the following functions discontinuous? All right. So if you look at this one here, right, f of x is equal to x squared minus x minus 2. Look, maybe you even recognize that, like, oh, the numerator will factor. It'll factor into x minus 2 times x plus 1 divided by x minus 2. I'll just cancel out the x minus 2's. Well, before you cancel out that, look, you still have to respect the domain of the original function. So we have discontinuity here at x is equal to 2 because you get a divide by 0 here. Okay, so you can't have a divide by 0. So now these are interesting, right? Like this one here is a piecewise defined function. Okay, it's saying it's equal to 1 over x squared when x is not equal to 0, and it's equal to 1 when x is equal to 0. So if you were to sketch this graph, this is what you would see. You know, 1 over x squared looks like this. And this is saying when x is equal to 1, when x is equal to 0, it's equal to 1. So it's like, look, this is from the left and right, it's increasing without bound, right? So there's definitely a jump. So even though the function here is defined when x is equal to 0, there's still discontinuity when x is equal to 0. And this is, again, you can just see because the limit as x goes to 0 of f of x, it just does not equal f of 0. And you get the same thing over here, right? Like if what I said is that this graph here looks like, you know, x minus 2 over x plus 1 divided by x minus 2. So this graph just looks like x plus 1. So if you were to sketch the graph of x plus 1, but there'd have to be a hole in it, right? Because, you know, you still got to respect the original domain here. So it would look like this. Then when you get to 2, there'd be a hole in the graph. And we're saying, hey, when x is equal to 2, it's 1. And you can see, like, it jumps down again. So again, we have discontinuity at x is equal to 2 here, again, because the limit of f of x as x approaches, again, 2 here, does not equal f of 2. All right, so just you know, kind of remember, like, you need to have this nice smooth, you know, you can't take your pen off the graph here if you want to have continuity. Okay, so it turns out, we've been talking a lot about discontinuity, but it turns out there are two types of discontinuity. Okay, so consider an open interval I that contains a real number c. So if a function f is defined on I, except possibly at c, and f is not continuous at c, okay, so then we say you have discontinuity at c, okay? So discontinuity falls into these two categories. So it turns out that like this type of discontinuity here is different from this type of discontinuity. So we have what's called removable discontinuity, and we have what's called non-removable. So a discontinuity at C is called removable if f can be made continuous by appropriately defining or redefining f of C. So these two examples here are what are called removable discontinuity. So look, we have discontinuity at C. But if I just redefine C, like if I can just, all I have to do is put a little simple dot in there, then that's called removable, because I can redefine C such that it makes it continuous. Okay, so removable. All right, because I just define C here, because I define f of C. In here, notice how I have this hole, but just a single point drops down. So if I redefine it by moving it up here, it's called removable discontinuity, because we redefine. So if you just, basically what's going on here is if you have a hole or just a single jump like this, okay, and I just move the single point back up here, then you have this what's called removable discontinuity, or removable discontinuity. This is an example of non-removable. So what happens here is like, even if I'm like, okay, let me redefine this hole here by opening this one up and closing this one, you still have, you still can't like have the pen go nice and smooth. You still have a jump. Like there's no way to redefine just a single point. So can't redefine to make continuous. Okay, so that would be an example of non-removable. Here's another one, right? Like if you just look back at that x squared, you know, just 1 over x squared, excuse me, f of x is equal to 1 over x squared. So like both of these butt up against a vertical asymptote. Like whenever you have a vertical asymptote that you butt up against, like there's no way you can redefine it so that it makes it continuous. So this is another example of non-removable. It's okay, so asymptotes also create non-removable discontinuity. I'm just going to put discon here. Okay, so we're going to do. I'll do some more examples of this. Okay, obviously, so you can see this in action here. Okay, so let's talk about these. Okay, so let's discuss the the continuity, or in these cases of the discontinuity of these. So if you were to look at the graph of 1 over x, so it's the reciprocal function, so it's literally going to look like this, right? Like, oops, I drew this wrong. Sorry, my bad. Just got ahead of myself here. So it looks like this. Sorry about that, guys. So notice it has a vertical asymptote at x is equal to 0 here, right? So there's no way I can redefine it to make it continuous, okay? So here we have discontinuity at, let's see, x is equal to 0. And in this case, it's non-removable. All right, but now if you look at this graph, right? So this graph here, this function here, you can immediately see that it's going to be like this. And you're going to notice that they're going to cancel out, right? These factors here. So this function looks like x plus 1, but you still have to respect the domain. So x cannot be equal to 1, okay? Because you plug in 1, you get to divide by 0. So this graph is going to look like this. When you go to x is equal to 1, there's going to be a hole in it, okay? And it's going to look like this. So there's going to be a hole in it. So we see here we have discontinuity at x is equal to 1. All right, right? It's continuous everywhere else, but just not at x is equal to 1. But notice how it's just a single hole in the graph. So like I could redefine this, okay, by just saying, oh, hey, let's just have f of 1 is equal to 2. So this is a case of removable discontinuity. Okay, so non-removable, you can't redefine the discontinuity, but removable, as you absolutely can redefine the discontinuity. All right, let me show you a function that maybe has both. Okay, it has some removable and some non-removable discontinuity. All right, so let's look at this one. All right. So consider this function. F of x is equal to x divided by x squared minus x. And let's find the values, if any, at which f is not continuous, and which of these discontinuities are removable. So look, when you look at this, right, you can see that it's going to factor in the denominator like this. Okay, you could cancel out the x's, and it literally looks like x is equal to, or f of x is equal to 1 over x minus 1, but you still have to respect the original domain. So like you cannot have x cannot be equal to 0, okay, and also x cannot be equal to 1, right? Because if you plug in 0 or 1 in here, okay, you'll notice that you get divide by 0. So if you were to sketch the graph of this, right? So here we know from pre-calculus, right, that the vertical asymptote is just going to be at 1 because I'm just looking at this. Okay, at x is equal to 0, what will happen is there'll be a hole in it, like this. And the graph is going to look like this. And you can see here, okay, we have discontinuity at the following. We have discontinuity at, sorry, it can't be negative 1, at x is equal to 0, and at x is equal to 1. But notice here, this right here, okay, if you were to plug 0 back into here, you'd get 0 over 0, you'd get the indeterminate form. So a lot of times here when you have the indeterminate form, you can see that it's the removable. But then here we have the vertical asymptote. This is non-removable discontinuity. Another way to help seeing it besides the indeterminate form is like, do you notice how I cancel out here that when x is equal to 0, I cancel out that factor that would make the denominator equal to 0. When you cancel it out, that's when it's removable. Notice that the x minus 1, which produces this discontinuity, x cannot be equal to 1. It was not removed. So I canceled out, I removed the x is equal to 0 product factor from the denominator. That would make the denominator equal 0, so it was removable. But also just remember, like if you plug 0 back in, you get 0 over 0. Indeterminate form means it's removable. All right, let's try another one. All right, let's look at this. So consider this function, okay? F of x is equal to x plus 2 divided by x squared minus x minus 6. So we can see that this will factor into, x minus 3 times x plus 2. So look, what values of x would cause a divide by 0? Okay, so we have discontinuity at, well, you cannot have x is equal to 3, right, because that would cause a divide by 0. And also, look here, you can't plug in a negative 2, okay, because that would cause divide by 0. But look, notice what I'm going to do then is I'm going to cancel out. So when I cancel out this factor, it's removable. And notice how I'm just left with the x minus 3, which means I have discontinuity at x is equal to 3. This is non-removable. And look, you could see, if you were to plug this in your graphing calculator, right, hopefully remember from pre-calculus, it's just going to look like this. So at negative 2, there'll be a hole in the graph. It's just going to look something like this. It's supposed to be a hole. So this is the removable discontinuity, and the vertical asymptote is the non-removable. Okay. So let's talk about this one next, okay? Let's consider this function. F of x is equal to cosecant of 2x, right? So we know cosecant is the same thing as 1 over sine, so this is the same thing as 1 over sine of 2x, okay? So find the x values, if any, at which f is not continuous. So look, this is the graph of cosine of x, not cosine of 2x, okay? And so what you see here is that we have vertical asymptotes. So when looking at this function, just x, okay, we see we have vertical asymptotes at every pi. So negative 2 pi, pi, 0, pi, pi over 2. So x cannot be equal to n pi, where n is an integer. So now when you have the 2x here, the 2, remember from pre-calculus, what this does is this is going to change the period. So, it works the opposite way you would think, because you have 2 times x. Well, what it does is it shrinks the period by this number. So it's going to shrink it by half. So when looking at f of x is equal to cosecant of 2x, what happens is x cannot be equal to n pi over 2. Okay, so every n pi over 2, and this is where n is an integer. Okay, so just remember your pre-calculus, like how this shrinks the period here. All right, so let's just look at these here and talk about the intervals on which these functions are continuous. Okay, so kind of like, just generally looking at them and being like, hey, what values do I have to have here? Okay, so look at this first one: x divided by x squared plus x plus 2. So like there's no real number here that'll make this here a divide by 0. So this one here is all real numbers, right? Okay, so this is going to be from negative infinity to infinity. Same with cosine of x. So if you consider the cosine, this is all real numbers. Next, when you look at this here, you can't have a divide by 0, and then you also cannot have a negative underneath the square root sign. So it looks like for this here, it has to be that x has to be greater than -1, right? Like, because if you had -1 in here, you'd get 0, and anything less than -1 here would be a negative under the radical. So here, what this would be is, where is this continuous? It's from -1 to infinity. And then here, what about this one? Well, you can't have a divide by 0, right? So for this one here, it's just x cannot be equal to 0, right? Because then you would get 1 divided by 0. You can't have that. But any other value of x works. Boom. Everything else works. Okay, and hopefully just kind of like looking at that, it resembles a some of your pre-calculus, right? Like just talk, this is kind of like looking at even just the domain here. Okay. Now we want to talk about one-sided limits, okay? So we write this. The limit as x goes to a, and then you see this negative sign here, okay? Of f of x is going to be equal to L, and then the limit as x goes to a with this positive sign here is equal to f of x equal to L, to signify the one-sided limits. So this first limit here, this one, is called the limit from the left. Okay, so let me show you what that means. Suppose you have this function here. It's just a parabola, okay? And this is the value x is equal to 3, okay? the limit from the left looks at values of f of x as x approaches from below. So this limit, as you just consider this one-sided limit, so just from below, this one here is the limit as x goes to 3 from below of f of x. So you're only looking at what's happening on this side of the limit, okay? Then this one here, the second limit, is called the limit from the right. Sometimes you'll hear me say from above. It looks at just this arrow here, like what's happening to the function as x goes to 3 from just the right-hand side, so from just above. So this is the left side, one-sided limit, and this is the right side. Okay? So sometimes you just want to look at one-sided limits instead of looking at them both together. And so what will happen is like for a limit to exist, the one-sided limits both have to agree here. Okay. But you know what you'll see here is we'll use one-sided limits in a bit to discuss continuity on a closed interval. Okay, so let's look at this one to discuss one-sided limits. So let's consider this function. F of x is equal to the square root of 4 minus x squared. Well, if you look at the domain, right, the domain of this function is going to be just between -2 and 2. Any values less than -2 or above 2 will produce a negative under the square root sign. So what this graph is going to look like, and if it helps to even just use our calculator here. I actually have it plugged in already, but so if you go to y equals, and we want to do the square root of 4 minus x squared, and then we look at the graph, you can see it's just a half circle, right? It's a half circle, okay, and the radius here is 2. Right, pretty terrible circle there, but you get the idea, or half circle. All right, so let's find the following. Let's find the limit as x goes to -2. Well, look, we can see you got to consider both sides for a general limit, right? So if you look at the limit as x goes to 2 from above, we can see that it looks like it's going to 0. But on the left-hand side, there's no graph to follow or to look at where it's going. So like you can't evaluate the general limit because there's no way to see where the graph is going. So there's no graph on the left side here. So because of that, because you're only able to see what's happening as you approach from above, this limit here does not exist. But if you look at just the one-sided limit, so the limit as x goes to -2 from above, so you're only considering as the limit on this one side, you can see that it looks like the graph is going to 0. So this is a case where the one-sided limit exists, but the general limit does not. And it's the same thing as x goes to 2. As x goes to 2, you can see what's happening from below, but there's no graph above. So there's no graph on right of x is equal to 2. So the general limit here does not exist. But again, if you just look at the values from -2 from below, so just this one-sided limit, you can see, oh yeah, it's going to 0. So look, to evaluate a limit, you need to have a graph on both sides of the value. But you can see here, you only have a graph to the right on this side and the graph to the left on this side. So when there's nothing on this side or nothing on this side, you can't evaluate the general limit, but you absolutely can evaluate the one-sided limits. All right, let's talk about these, okay? So use the graph to determine each limit and discuss the continuity of the function, okay? So look, for each of these functions here, I want to find the limit as x goes to c from above, as x goes to c from below, and just the general limit, okay? So here, this graph is my function. The limit as x goes to c from above of f of x. Well, so my c is my -3. So as I look at values above, it literally looks like, I'm just only looking at the one-sided limit, it looks like it's going to 3. If you look at the limit as x goes to c from below of f of x, it also, just from the left, only from the left, that's what this one-sided limit means, it also looks like it's going to the value 3. And in this case, the limit as x goes to 3, or goes to c of f of x, so just the general limit here, as you're going to negative 3 here, it's also 3. But you can see here we have discontinuity. Add x is equal to c. And in this case here, just because it's a single point, it's removable. Okay, so for this one here, here's our graph, okay? And our value is c, or our value here is c is equal to 2. So I want to find the limit as x goes to c from above of f of x. So that means values from the right. So look, I'm only looking at this one-sided limit. So where does it look like the graph is going? Looks like it's going to negative 3. Okay, because I'm only looking at the right-hand side. So now if you look at the limit as x goes to c from below, I'm only looking at the left-hand side, and it looks like it's going to the value 3. But then if you look at the general limit, so the limit as x goes to c of f of x, you can see it does not exist because the one-sided limits go to different places. And because of that, you can see here that the jump here, we have discontinuity at x is equal to c, and it's non-removable. Okay, it's non-removable. So very interesting, right? Like in this case, the one-sided limits agreed, and you saw that the general limit was 3. Here you see that the one-sided limits do not agree. Okay, one-sided limits do not agree, and the general limit does not exist. And that's okay. That's okay. Okay, let's try these, okay? Find the limit if it exists, and if it does not exist, explain why. So look, let's look at the limit as x goes to 3 from above of this right here. So look, we see that x cannot be negative 3, right? So in this case here, if you can just plug it in, like if I could just plug 3 in, all right, even though it's a one-sided limit, if I can just plug it in, do it. So if you can plug in, and the value is in the domain, that's okay for a one-sided limit. Here, if you look at this, like if you just try to plug this in, okay, this 4, so even though I'm saying find the value as you go from 4 below, even if you just try to plug this in, you see you'll get 0 over 0. Okay, so you'll get the indeterminate form. So you're going to have to rationalize the numerator here. So you get the limit as x goes to 4 from below. So FOIL, right? But the middle terms cancel out. Square root of x times x gets me x. Minus 2 times 2 gets me minus 4. All over x. Check that out. It's going to cancel out. So the x minus 4 cancels out. And look, now you can just plug 4 straight into this, right? So this finally just becomes 1 over the square root of 4 plus 2. Gets me 1/4. So, because square root of 4 is 2 plus 2 gets me 4. So you can see here, like, even you can still use the same principles to evaluate one-sided limits. Like that's okay. Totally okay. And now look, if you look at the cotangent of x as x goes to pi, like here's the graph, you can see you have a vertical asymptote here. So like, you know, this limit just does not exist. And you can just see here it's because the one-sided limits increase and decrease without bound here. Okay, so your vertical asymptote. All right. let's talk now about continuity on a closed interval. Okay, so we've looked at an open interval in the definition of continuity at a point. So here, a function f is continuous on a closed interval when f is continuous on the open interval, okay? And look, the one-sided limit as you go to a from above, so that's the bottom point, so you're looking as you come from above of f of x is equal to f of a, so you can just plug it in. And the limit as x goes to b from below, all right, of f of x is just equal to f of b. So here the function is continuous from the right, and the function is continuous from the right at a, and continuous from the left at b. And if you have this case, what you're able to say is the function is continuous on the closed interval. Okay, let's go back and let me do an example to explain this here. So let's do this one here. Let's discuss the continuity of this function again, okay? So this is what the graph looked like, okay? So what I want to show you is that we said the domain here was from -2 to 2. So I want to show you that it's actually continuous on the closed interval from -2 to 2. So this is my A and this is my B in the formula here. Okay, so let's look at the limit from above as x goes to A from above of f of x. So if you look at the limit as x goes to -2 from above of f of x, well look, we saw that that exists and it's equal to 0, okay? Which is also what f of -2 is. It's 0. Checks out. Boom. Now if you do it the other way, the limit as x goes to 2 from below of b, okay, so that's b, 2, of f of x, we see, boom, right here that that exists and is equal to 0. And it's the same thing as f of 2, okay, or f of b here. Thus, what we see here, we have a continuous, or we have continuity on the closed interval from -2 to 2. Okay, let's end this lecture talking about, just real briefly, I just want to introduce this thing called the intermediate value theorem, and then I just want to show you one quick example of it. So f is continuous on the closed interval from a to b, and f of a is not equal to f of b. Okay, so let me show you what that looks like. Okay. All right, so here's a, here's b, and maybe the graph looks something like this. Okay, so here's f of a, here's f of b. Okay, all right, you can see it's definitely continuous there. And what you're going to see here is k is any number between f of a and f of b. So this, like, k might be like right here. Okay, so k is between f of a and f of b. Then there has to be at least one number c between a and b, such that f of c is equal to k. All right, that's it. That's all this is saying. And look, all the intermediate value theorem tells us is that the number exists, not how to find it. Okay, this is just called an existence theorem. You will find that a lot of proofs might just say, oh, by the intermediate value theorem, this has to hold. So it just means that like this value c exists. I just don't know how to find it. Okay. Let me show you a quick example of this intermediate value theorem. All right, so let's look at this. Use the intermediate value theorem to show that f of x, which is equal to x cubed plus 2x minus 1, has a 0. Okay, so that means it has an x-intercept in here. Okay, an x-intercept between 0 and 1. So look, this is my a, and this is my b. Well, look here. If you plug f of 0, okay, you get 0 cubed plus 2 times 0 minus 1. You get negative 1. If you plug 1 in, okay, you get 1 cubed plus 2 times 1 minus 1. All right, well, that's 1 plus 2 is 3. You get 2. So look, I have no idea what this graph has, but look, f of 0 is not equal to f of 1. Okay, so that what that means is there has to be a value between negative 1 and 2, which is the 0. Okay, thus because, okay, what you have here, f of 0 is equal to negative 1, which is less than the 0, which is less than f of 2, okay, which is equal to 2. The intermediate value theorem tells us that f of x must have a 0 between 0 and 1. And that's all that's saying, right? Like, I don't know what this graph looks like, okay? But look, I know that the graph, when you plug in 0, it's equal to negative 1. And when you plug in 1, it's equal to 2. So the only way the graph can be a function and go through these two numbers is that it must have a 0 somewhere between 0 and 1. And that's what the intermediate value theorem helps us see. All right, class, as always, you'll get a chance to practice all this on your homework, and I hope this lecture was helpful for you.